Today, we want to start finding some antiderivatives. We saw from the fundamental theorem of calculus that we can calculate a definite integral using the antiderivative. That's the capital F of B minus capital F of A. The definite integral of a rate of change of a function gives a total change in the function. We also saw that we could construct antiderivatives using the definite integral. Those are the two parts of the fundamental theorem of calculus. It goes both ways. Use the definite integral to calculate to construct an antiderivative. Use the antiderivative to calculate the definite integral. Just because we lead with that does not make finding antiderivatives an integral part of calculating definite integrals. If we want fast, accurate, efficient ways for calculating definite integrals, we have better ways than doing antiderivatives by hand. But if we can't find antiderivatives by hand, we have a really hard time having any kind of discussion in future math classes. We could talk about calculus ideas without anybody having any background in algebra, but it's really difficult. And we really have to modify things, and its usefulness is very decreased. So let's find some antiderivatives. Yesterday, we talked about the big one, the integral of x to the n dx is 1 over n plus 1 times x to the n plus 1 plus c. Add 1 to the exponent, divide by the new exponent. Those are the words that go along with this. Add 1 to the exponent. Divide by new exponent. This is the inverse. The reason I like to start with this is that this is the inverse of the process that we learned for derivatives. For derivatives, the derivative of x to the n, we multiply by the exponent and then subtract 1 from the exponent. So if we're going to invert that process, we do the inverse operation in reverse order. The last thing that happened is we subtract 1 from the exponent. So inverting, the first thing that happens is we add 1 to the exponent. In derivatives, we lead with multiply by the exponent. So the last step in antiderivatives is to divide by the new exponent. So this is just the inverse of the derivative rule. This is just the inverse of the derivative of x to the n is nx to the n minus 1. We put a plus c on because the derivative of every constant is equal to 0. So when we're trying to undo this derivative process, we don't know what any constants might have been there before. So this is called the constant of integration. That's our constant of integration. This is the constant that was lost when we took the derivative. So we have to have the plus c because the derivative with respect to x of a constant is equal to 0. Like we saw yesterday, we can't have n be -1 in this process. So because of this part happening right here, the 1 over n plus 1, we can't have an x to the -1. So this only works for n when it's not -1. But that's okay because we have an answer for the integral of x to the negative 1. What is the integral of x to the negative 1? Remember what we're doing when we're finding antiderivatives is we're turning around things that we know about derivatives. The derivative of natural log of x is 1 over x. So the integral of 1 over x is natural log of x. I threw y'all off a little bit because instead of writing 1 over x, I wrote x to the negative 1. There's some extra trappings that we need when we turn our derivative statements into integral statements. In particular, we need a plus c. Another thing that we want to note about the function we start with and the function we end with is that they don't have the same domain. The domain of x to the negative 1 is anything that's not 0. The domain of natural log of x is only positive. I can't have a natural log of negative x. But if we look at, well, I'm just going to write it. If we include absolute values around our x, now the domains match and the statement is still true. So now we've covered up the gap that showed up in our first one. When we have x to the negative 1, we'll use natural log of x, absolute value of x. X to the anything else, add one of the exponents, divide by the new exponent. Any questions? Okay. I know some of you are thinking, dude, we got this far last semester. Even if you weren't in my class, we got this far last semester. But you always got to overlap them a little bit. The previous class, you never assume that everything in the previous class is still in place when you get to the next class. I know this is true because I've been teaching calculus for a very long time. And I promise you, there's a whole bunch of algebra that y'all ever didn't even heard of. Whatever your grade in algebra was. You'd be like, oh, no, I'm good at algebra. I got an A always through an algebra. And I need to say, I promise you, you're not as good as algebra as you think. You've been good enough, but there is no algebra class that will just actually prepare you to the point where just going through that class will have you remember that algebra forever. That's just not how it works. You know what I mean? I'm probably pretty sure that some of you probably still use the quadratic formula to solve quadratic equations, and you're not embarrassed by that. I'm just kidding. You shouldn't be embarrassed by using the quadratic formula. Except for the fact that you're Calc 2 students and you need to find a better way. And I'm not talking about calculators. You need to understand parameters better. The quadratic formula is trash. So is PEMDAS. PEMDAS is trash. That's all beside the point. We can now integrate any power of x. So let's look at some examples. When I want you to do this process, I'm either going to ask you to find the antiderivative. I might say find the general antiderivative. The general antiderivative is the one with the plus c. When I call for the general antiderivative, I'm going to want you to use rules for finding antiderivatives. To find the antiderivative, and the general part is put a plus c on the end of it. Or I could just write the indefinite integral. So I could say, what's the indefinite integral of x to the third dx. Note that the dx is part of the punctuation. At this point in your career, just think of the dx as being part of the punctuation. Don't just write integral of x cubed, write integral of x cubed dx. Remember, we're adding up a bunch of rectangles, length times width. Don't forget the width. What's the integral of x cubed dx? Well, it follows a pattern. N is equal to 3. And the process is to add one of the exponents, so 4, and then divide by the new exponent, 1/4. Some of you might have been brought up in a slightly different notational convention. And so you might want to write and even think and say x to the 4th over 4. Integral of x cubed is x to the 4th over 4. Some of you is going to think that's weird. And you're going to say, no, 1/4 x to the 4th. And some of you will look at me like when I said 1/4 x to the 4th, like, oh, that's weird. What's wrong with you? It's x to the 4th over 4. They are equal. One of them you will remember better than the other one. So just figure out which one that is, and that's the team that you're going to be on. What if I write 1 over x to the 5th? What does this look like as a power of x? Yeah, we can replace 1 over x to the 5th with x to the -5. If we can write powers of x, then we should write powers of x. So I'm going to write 1 over x to the 5th as x to the -5. Now, I can use the rules that we just developed. Add 1 to the exponent, divide by the new exponent. Tricky part here, -5 plus 1 is -4. I know you're all thinking, I would never make that mistake. And I promise you, like we had a quiz on this on Monday. Statistics indicate that 1/3 of you would take -5, add 1, and come up with -6. I wouldn't make fun. These are just facts. So I have a -1/4 x to the -4 plus c. We could simplify this negative exponent. But we don't gain a lot out of it. Although we should be aware that this is equal to the x with the x to the 4th in the denominator. So that's how we would simplify the negative exponent. I do not require, if you're writing things down for me, I do not require that you simplify negative exponents. Negative exponents are okay. Fraction exponents are okay as well. What can we do with the square root of x? How can we write that so that we could use our rules? X to the 1/2 power. If we can write powers of x, then we should write powers of x. Once I have x to some constant, I add 1 to the exponent and divide by the new exponent. 1/2 plus 1 is 3/2. 1 divided by 3/2 is 2/3. Add 1 to the exponent, divide by the new exponent. This problem was originally stated in radicals. It's perfectly acceptable to leave your answer with fraction exponents. Fraction exponents are much better. we look a little bit old-fashioned if we start writing in radicals. Let's be modern and embrace the fraction exponent. This looks archaic to me. It's so weird. Once we realized that radicals represented fraction exponents, it would have been really handy if we're just like, oh, dude, we should just start running fraction exponents. Then all our exponent rules make sense. I think there was a bunch of old-fashioned people. It's like, oh, I like right, radicals. It's old-fashioned. It's traditional. It's the way we've always done things. The most sinister of all arguments. That's the way we've always done it. Once you make that observation, the next thing should be like, oh, wait, that probably means it's time to change. If no one says that, then things are probably going fine. But as soon as someone questions a process and the only answer that anybody comes up with is like, well, that's the way we've always done it. And then the other person's like, well, that's my point. We should change it. You know what I mean? Anyway. So ultimately, I'm okay with fraction exponents. I like them better. Let's have an instinct test. What's the integral of 5x to the third? 5 over 4, x to the 4. I didn't have to tell you that if you have a constant multiple, you just carry that along. We're just inverting the process of derivatives. So we should also just carry along our constant factors. The derivative of a constant times a function is that constant times the derivative of the function. So it makes sense that the integral of a constant times a function is that constant times the integral of the function. Keep your constant factors. Just like derivatives. Keep your constant factors just like derivatives. I didn't have to tell you that was a rule. You just guessed that that's how it should work. It's great in math when how you think it should work is how it should work. Question? So when we have x to the 1/2 power, where our process is to add 1 to the exponents and then divide by the new exponent. So the 1/2 plus 1 is 1.5 or 3/2. So 1/2 plus the 1 is 1.5. I spelled 2 wrong. Or 3/2. And then we divide by the new exponent. So if we're dividing by 3/2, that's the same as multiply by 2/3. So that's how we go from the radical, the 1/2 to the 1/2 power, add 1 to the exponent, divide by the new exponent, and there's our antiderivative. We can check that this is the case by taking the derivative of our answer, see if we get back to where we started. 3/2 times 2/3 is 1. 3/2 minus 1 is 1/2, just like we planned. So you can always take the derivative of your answer to see if it gets you back to the original. The derivative of minus 1/4 x to the minus 4, -4 times -1/4 is 1. -4 minus 1 is -5. That derivative got us back to the start. So we know we're right. Any questions? In the previous one, we discovered that we can keep constant factors just like with derivatives. In this integral, I have two terms. I've got a 3x to the negative 5 minus 7x to the 1/2 power. So if you're thinking, why don't we just do this a term at a time? Your instincts are correct. Just like with derivatives, if you want to take the derivative, you take the derivative a term at a time. Same with integrals. We're going to read the 3 over x to the 5 as 3x to the negative 5, just like before. And we're going to read the 7 square root of x as negative 7x to the 1/2 power. But then we just follow the same rules we had before. I keep the constant multiple of 3, the constant factor of 3. The integral of x to the negative 5 is negative 1/4 x to the negative 4. I keep my constant factor of negative 7. And the integral of 1/2 is still 2/3 x to the 3/2. And then I just simplify. Negative 3/4 x to the negative 4 minus 14/3 x to the 3/2. So we can do term by term antiderivatives, just like derivatives. Go term by term, just like derivatives. Questions? So the idea here is that if we can write things as in terms that are powers of x, then we should write things as terms that are powers of x. Sometimes it's convenient to do so, and sometimes it's not. But for example, I want x cubed minus 2. I started thinking about the 2. And the 2 manifested itself as a term. I did not want that term. Let's go x cubed minus 5 squared. That was one of those situations. I was writing x cubed, and then I wrote minus, and I'm like, oh, don't write 2. You're going to use that for the exponent. And then the signal came through. It was like, oh, write 2. That's all I heard. Write 2. I'm like, oh, no, I wanted a 5. And my hand was like, oh, well, then you shouldn't have said 2. So we don't know how to integrate when we have this composition of functions. We've got this x cubed minus 5, and it's being squared. So we do have the term by term thing. So let's just use that. We'll use We'll multiply this out. We'll take x cubed minus 5 and just square it. So I have an x to the 6th minus 5x to the 3rd minus another 5x to the 3rd plus 25. So instead of integrating this weird square, we'll just rewrite this as terms with powers of x. Now that I've got terms, we can add 1 to the exponent and divide by the new exponent 3 different times. So we were not originally presented with terms that are powers of x, but all we had to do was use the distributive property, and that got us to terms with powers of x. Any questions? We just use the distributive property to get terms that are powers of x. Here's another example where we could use the distributive property to get terms that are powers of x. All 3 of these things are being divided by an x squared. So I can just distribute the 1 over x squared to the 3 terms. I can think of this as x squared over x squared minus 3x over x squared plus 5 over x squared. Then I can just simplify each of those terms, and I'll have terms that are powers of x. X squared over x squared is 1. 3x over x squared is 3 over x. 5 over x squared is 5x to the negative 2. Now I got a bunch of terms that are powers of x. I left the x in the denominator to help remember that x to the negative 1, the integral of x to the negative 1 is natural log of x, but we normally say 1 over x instead of x to the negative 1. But now we can just go a term at a time. The integral of 1 dx is x minus 3 times the natural log of the absolute value of x minus 5x to the negative 1 plus c. In both these examples, we just use the distributive property to write terms that are powers of x. Any questions? All right. Question. The dx, that represents the width. Remember, we're thinking right now, we're thinking about integration as finding area under the curve. Area is going to be length times width. The length is the value of the function that keeps changing. The dx comes from the delta x. Those are all the widths. But when we go to an infinite number of rectangles, they become infinitely thin. So the delta x becomes the dx. So our discrete delta x becomes the continuous dx. So think of it as part of the punctuation. It's also telling you what's the variable in this expression. So if I have like mx plus b, but then it says dx, that tells you that m and b are both variables, and it's x. Sorry, m and b are both constants, and it's the x that's the variable. So that's the other thing it's there for. All right. Well, this finding antiderivatives analytically is chapter 6, section 2. So that's where you're going to want to go to reinforce this skill. That's going to do it for today. That's going to do it for this week. Everybody have a good weekend. I'll see y'all on Monday, and thanks for playing.